This video is about slope. Now, this is somewhat of an introduction to slope. There are many applications that we'll eventually be building on with this topic. But for now, we're just going to start from the ground up. And to do so, we'll begin with an XY coordinate plane drawn. So we have a vertical axis, which is our y-axis. We have a horizontal axis, which is our x-axis. Those are familiar labels to us. And then on the x-axis, we're going to mark two places, x sub 1 and x sub 2. So sub means subscript, and it's just a way to describe two different variables here. So x1 and x2, and they're just spaced out on the x-axis, really in an arbitrary location. We don't have actual grid numbers or lines on this coordinate plane at this point. We're just kind of freehanding this. So we have x1 and then x2, where x2 is further down the line. And then on the y-axis, similarly going upward, we have y1 marked on it, and then y2, where y2 is above y1. So again, those are arbitrary markings, but the picture is what's going to be useful for us here. And so you can see that if you connect or find the place where the point x1 comma y1 is, that would be a location in this coordinate plane. You could put a point there with those coordinates x1 comma y1, and similarly you could find the point whose x coordinate is x2 and whose y coordinate is y2, and that would be the point x2 comma y2. So you could put those 2 points in the coordinate plane even without knowing what actual numbers those letters or variables represent. Then if we connect those 2 points to form a line segment, we get this kind of slanted looking line segment. And what we're going to do next is draw a triangle which uses the line segment we just made as its hypotenuse. So it's a right triangle, which means vertically we'll go straight down from the point x2 comma y2 straight down, and then horizontally we'll go from the point x1 comma y1 straight over, in this case to the right, and we'll do so to form a right triangle in our picture, in our coordinate plane. Once we do that, we're going to give some extra labels here. We're going to call the horizontal distance all the way across the bottom of this right triangle, we're going to call that the run. Okay, just as a convenient name here. Run representing horizontal distance. And similarly, we're going to let the vertical distance be described as the rise. So we have rise as that vertical distance. Again, those words are just kind of descriptive and useful. Rise typically means something going up and down, so vertical distance is rise. Now, we wanted to enter a definition here, which is that for slope. Now, typically slope is abbreviated with the letter m, and we're going to define it as the steepness of a line. Now, we can give a mathematical definition of it as the ratio of rise, remember that was our vertical distance, over or divided by the run. Remember that was our horizontal distance. In this picture we've been drawing this diagram. And furthermore, we can define those actual measures or lengths mathematically with a very useful formula that we'll be using over and over again, which is this: y2 minus y1 over x2 minus x1. So this is going to be what you could call our slope formula for finding the slope given two coordinates. In this diagram, we have the coordinates x1 comma y1 and x2 comma y2. Normally, in an example, those would be actual numerical values. You could plug the coordinates of those points in for all these variables, x1, y1, x2, y2, and in so doing, get a simplified fraction or ratio out of it. That is how we define the slope of a line segment given those 2 points. Now, let's actually practice this with some examples. The first set of them is asking us to find the slope of each line from a given graph. Now, in the first graph, of course, we have an xy coordinate plane where the x-axis is horizontal, the y-axis is vertical, and we have 2 points plotted here. They're actually the intercepts. So we have a y-intercept at the point 0, 3, and we have an x-intercept at the point -2, 0, and then a line segment connecting them. Well, as we've seen, that's a way to draw a line, but at this point, we're really more interested about the slope of each line. As we saw above, we can find that by understanding what the rise and the run is of the slope segment, or you could say the triangle that we have in this picture. So you could understand a right triangle to be such that the rise would be the distance from the origin up to the y-intercept. If we call that the rise, the vertical distance, then that would be a measure of 3 units. Similarly, if we call the horizontal distance from the x-intercept to the origin, if we call that the run, then that distance, of course, is 2 markings, and then we have that being our run. So let me write that on here. We have run equals 2. Well, with the rise and the run extracted from the picture, we could then compute the slope by saying m equals, that's slope, rise over run. Well, rise is 3, run is 2, and so 3 over 2 would be it. That is the slope of that line. You can leave it as a simplified improper fraction. There's no need to write that as 1.5. In fact, you will most likely just see it as a simplified fraction, even if it's improper. Let's try a second example. This one is also a graph drawn with an x-axis horizontally, y-axis vertically, the typical coordinate plane. And in this case, we have a y-intercept at 0, 1, and an x-intercept at 3, 0. So we can pick out the rise and the run from this graph just like we did before. The rise would be just 1 unit going up to the y-intercept, and the run would in this case be 3 units going over from the origin to the x-intercept, which means we could say slope m equals rise over run, that's 1 over 3. So our slope would be 1/3. Now, there's one other item to recognize here, which is this. And we're going to finish with these definitions and go back and fix our slopes here if we need to. So we're going to add these 2 definitions. Positive slopes increase from left to right. Okay, the order matters there, left to right. And then we'll say negative slopes decrease also from left to right. So go back now to the 2 slopes we just found and determine should either of those be negative. We wrote them both as positive values, just picking out the rise and run as distances. Remember, distances are just positive, but maybe we have to adjust one of them based on these definitions. Well, notice that our second example is an example of a line which decreases going from left to right. It kind of goes down. If you were walking on the line, you'd be going downward as you go from left to right in this second example, which means we actually need to mark that slope as -1/3. So I'm going to sneak a little negative sign right in front of that 1/3 so that we understand that slope is actually -1/3. We do not have to do that for the first example here to the left of it, because that slope was increasing going upward from left to right, which means it is a positive slope. It can stay as +3/2. So sometimes the sign of a slope can be easy to miss or forget to consider, but it really does correlate with the direction of the line as you go left to right, as these definitions now say. Let's try an example which says this: find the slope of the line passing through the points 6, -4 and 4, -2. So we're given 2 points here, and notice there is no coordinate plane drawn for this one. We don't even need that though, given what we know above. In fact, we know that we can define slope as our formula m equals And now we said it's rise over run, but then more specifically with coordinates, we said that would be y2 minus y1 over x2 minus x1. Yes, it's easy to accidentally flip those or mix them around and somehow put the x's on top, but that's not the way it goes. You'll notice above in the definition, the y's go with the rise. I like that because it rhymes and it's easy to remember. Remember, it's a rise over run, y's go with rise, so we have y's on top, x's on the bottom. Now, all we have to do is label the two given points according to these coordinate values and then plug them in. Remember, these are not intercepts because they do not include any zeros for the coordinates, but that's okay. All we have to do is label them as x1, y1 and x2, y2, and it doesn't even matter which one you pick for which. Now, I'm going to be simple and just call the first one the ones. So I'm going to just label underneath the point 6, comma, negative 4. I'm going to write the label x1, comma, y1, representing that point. And then, of course, I'll label the other point as the 2's. So the second point, which was 4, comma, negative 2, we'll call that x2, comma, y2. And yes, it's possible even to get these all mixed up, so be careful. Make sure your 1's are together and your 2's are together. It could be tempting to put x1, comma, x2 as a point, but remember, every point has an x and a y in it, and we keep the 1's together and the 2's together. Well, once labeled, all we have to do is extract each value and plug them in for all the variables in this slope formula. So in the numerator of our slope formula, where we have y2 minus y1, we're going to replace the y2 in our formula there with the value we have for y2, which directly above the label is our negative 2. So I'm going to put a negative 2 in for y2. And if you want to be super careful, then put parentheses around it. Then we put a subtraction sign to match the subtraction sign in the formula there. And then after it, we put our y1 value, which again is the number directly above the y1 label. So in parentheses, I'm going to put now negative 4. Now this is where parentheses are really useful after the subtraction sign because they help maintain all the positive negative rules here. And so as you can see, we now have the now we have the y2 and y1 values in place as taken from the labels in our points. Now we go down below and do the same thing with the x's. Well, x2, directly above that, you see the number 4. So we put in 4 for our x2 value minus, now we want x1. Well, again, directly above that, we saw the value 6. And notice it's a positive 6, so we put that into blank parentheses. And then we simplify. In our numerator now, we have negative 2 minus negative 4. Well, remember, that's really negative 2 plus 4. I'll write it that way first, just to be clear. And then down below in the denominator, we have 4 minus 6, which we can just leave as 4 minus 6. Let's take this a little further. In the numerator, we have negative 2 plus 4. That's really just 2. In the denominator, we have 4 minus 6. That's negative 2. And of course, 2 over negative 2 will reduce to negative 1, which would then be our overall result for our slope. You can write it as negative 1 over 1, but there's really no need. That's simply negative 1, and we can leave it as that. Now, let's add some definitions to this, and that is, first, parallel lines have the same slope. Okay, so parallel lines would be lines that run together. Think of like the letter L's in the word parallel. Parallel lines just run in the same direction. But what we're saying here in this definition is that parallel lines have the same slope. Or secondly, we could say the slopes of perpendicular lines are what we call opposite reciprocals. So two words, opposite reciprocals. Opposite means different signs, so one positive, one negative. And reciprocals means kind of flipped over. We've seen that word used already in the past. So let's get down to some examples of this. Remember, if you had 3, then the opposite of 3 would become negative, and the reciprocal would be flip it over, so 1 over 3. So an example set of opposite reciprocals would be 3 and negative 1/3. The signs are different, and they're flipped over. Another example could be negative 4/5 and positive 5/4. Again, notice they're opposite signs. One's positive, one's negative, but they're flipped upside down, which makes them both opposite and reciprocals. In any pair of opposite reciprocals, like we've seen in those two examples, you will usually find that one of the pair is a fraction. However, there's one kind of different pair that sometimes throws people off, which is that the numbers 1 and negative 1 are actually examples of opposite reciprocals, even though they don't show up as fractions in either case. That's because, of course, 1 over 1 is just 1, and when you flip it over, it's the same thing. So that's a tricky pair I like to put down just to remind people that 1 and negative 1 do count as opposite reciprocals, which means any of these pairs could work as slopes of perpendicular lines. Remember, perpendicular lines meet at a right angle, and that's what it means to be perpendicular. Now let's do an example where we determine whether the lines passing through each pair of points are parallel, perpendicular, or maybe neither. And we're doing this given the definitions we just wrote above. Now we have two pairs of points described here. We'll go ahead and list them and then actually work with them. The first pair is the points negative 2, negative 7, and 3, 13. So that's a pair of points that would be on some given line. We want to find the slope of that line, and so we'll go ahead and use our slope formula, which means m equals, and then if we label them like we labeled above, where the first point is the 1's, x1, and then y1, and the second point is the 2's, so x2 and y2, then we can just plug them all in according to that formula. So in the numerator of the slope, we have y2, which is 13, minus y1, which is negative 7. Be careful to put that in parentheses there to catch the double negative there. So we have 13 minus negative 7. That's y2 minus y1. Down below, we have x2 minus x1, which would become 3 minus negative 2. Again, watch the double negatives there. If we simplify this, in the numerator we really have 13 plus 7, and in the denominator we have 3 plus 2. So in the numerator that means we'll have 20, in the denominator we have 5. So the slope of this first line given by its pair of points would be 20 over 5. Now you could even reduce that, that's just positive 4. Okay, but we want to compare that with the second line segment. Now those points are given as the following ordered pairs. We have negative 1, negative 9, and 5, 15. Again, if you label those, we'll pick, again, just x1 and y1 as the first pair, and x2, y2 as the second pair. Then for that line, we could say m equals, and then y2, which would be 15, minus y1, that would be minus negative 9. And then down below, we have x2, which is 5, minus x1, that means minus negative 1. So again, be careful with the double negatives, and the parentheses really help with that. That means in the numerator we have 15 plus 9, which is 24. And in the denominator we have 5 plus 1, which is 6. Of course, you can reduce. 24 over 6 is 4. Okay, so let's try to conclude what's going on here, right? The question we were working on said to determine whether the lines passing through each pair of points are parallel, perpendicular, or neither. Well, directly above we have our definitions for parallel and perpendicular, and notice both definitions involve the slopes. So if our slopes meet the definitions, that'll tell us. If they don't meet either definition, that would mean neither. We'll notice that we just computed both slopes to be 4. And since those are the same, we go up and recall that the same slope means these are parallel. So same slopes, parallel lines. We can tell simply based on the slope calculations that these lines, which you could form by connecting each pair of points, would be parallel lines. Let's try another example of the same type. This time we have our first pair of points given as negative 2, negative 15, and 0, comma, negative 3. So we'll want to compute the slope of those points, again labeling them as x1 and then y1, and then x2 and y2, just kind of going left to right, picking that order. That means the slope of the line that connects these first two points, the first pair of points, will be, let's see, y2, which is negative 3, minus y1, which is negative 15. So again, be careful with parentheses. We have negative 3 minus negative 15, over x2, which is 0, minus x1, which is negative 2. So 0 minus negative 2. Okay, if we simplify and crunch those out in the numerator, that's really negative 3 plus 15. That's a positive 12. In the denominator, that's 0 plus 2, which is positive 2. So really we have 12 over 2, which is a positive 6. If we go on to our next pair of points and compute its slope, we have the first point being negative 12, comma 6, and the second point being 6, comma 3. So let's go ahead and label those in like manner. We have x1, y1, and then x2, y2, and we can compute that slope in the same way. y2 is 3, y1 is 6. So y2 minus y1 is 3 minus 6. Down below it, x2 minus x1 would become 6 minus negative 12. And then we'll want to go ahead and simplify this. In the numerator, we have 3 minus 6. That's a negative 3. In the denominator, we have 6 minus negative 12. That's a positive. That's like 6 plus 12, so 18, which means our value, when simplified, would be negative 1 over 6. 3 over 18 simplifies to negative 1 over 6. If you then conclude by comparing the slopes of 6 and negative 1/6, you'll say, wait a minute, those are opposite reciprocals as we defined above. So that means we have perpendicular lines by definition above, given that those are opposite reciprocals. Let's try yet another example. In this case, we have the first pair being the points 0, comma 3 and 0, comma negative 2. So again, we'll go ahead and start here labeling this x1, y1, x2, y2, and then compute slope as m equals y2 minus y1, that's negative 2 minus 3, x2 minus x1, that's 0 minus 0. And so if we try to simplify that, we'll get negative 5 over 0, but that's interesting. That's actually a value known as undefined. Okay, we've seen this kind of thing before. You cannot divide by 0, a number by 0. So we call that undefined. Okay, so just leave that there for a second. Let's go on to the next one and come back and try to make some more sense of that. The second pair, which of course is the points 3, comma 6 and negative 7, comma 6, if we label those and compute the slope the same way, our slope here will be 6 minus 6 over negative 7 minus 3. That's just using the formula we have defined above, which means we have 0 over negative 10. Now, it's okay to divide 0 by a number, which is contrasted from the first slope we just computed, where you're dividing by 0. Here you're dividing 0 by a number. 0 over negative 10 is just 0. So we have, interestingly, an undefined slope and a 0 slope. Well, we have two special cases of lines here that we want to understand, and it's not obvious based on our definition of parallel and perpendicular that we wrote above. So we're going to use some additional definitions here. We'll define it as follows. A vertical line has undefined slope. Okay, so that means in our example here, the first pair of points is actually on a vertical line. Additionally, we can add another definition, which is this. A horizontal line has slope equal to 0. So these two definitions are always true, which is why it's good to note them. And that applies directly to our problem here, which means we have in the first pair a vertical line, and in the second pair a horizontal line. So though these slopes aren't obviously opposite reciprocals, because one's undefined and one's 0, and that doesn't quite fit the simple change the sign and flip it over definition of opposite reciprocals. But since we know what we know about vertical and horizontal lines, we could say, so these are perpendicular.